Picture this. A warhead-equipped kamikaze drone, cheap, deadly, and virtually impossible to stop, is streaking toward a target at over 100 knots. It is not guided by GPS. It is not communicating over a radio frequency that can be jammed by conventional means. It is bouncing signals off a mesh of over 10,000 satellites orbiting roughly 300 miles above the Earth, switching connections dozens of times a second, encrypted, authenticated, and invisible to every electronic warfare system currently deployed in a major adversary's arsenal. The drone costs approximately $35,000. The systems designed to defend against it are rendered useless. That is not a hypothetical scenario or a piece of speculative fiction. That is what occurred on the 28th of February in the year 2026, when the United States military unleashed a new weapon in combat for the very first time. A weapon that has since sent the military analysis circles and open-source intelligence communities of its adversaries into a state of full-blown panic and self-reflection. Today's subject is one of the most significant developments in modern drone warfare documented to date, and the situation is evolving at an extraordinary pace. The weapon causing this profound unease is designated LUCAS, an acronym for Low-Cost Uncrewed Combat Attack System. It is manufactured by a relatively obscure Arizona-based defense startup called Spectre Works, and it made its combat debut during a major coordinated operation against Iranian military infrastructure on the 28th of February. Central Command confirmed that LUCAS drones successfully struck command and control facilities, air defense nodes, missile and drone launch sites, and military airfields across a wide operational area. What is perhaps most stunning about this system is not just its capability, but the speed of its delivery. 7 months earlier, on the 16th of July of 2025, the Secretary of Defense had publicly unveiled the LUCAS platform on the grounds of the Pentagon. A timeline of 7 months from public unveiling to active combat deployment is something that would have been unthinkable in the traditional and often cumbersome acquisition processes of past decades. There are legacy systems within the inventory that require decades to move from the drawing board to the battlefield. Spectre Works and the supporting Pentagon offices accomplished this transition in approximately 43 weeks. That acquisition speed tells a story about the urgent strategic necessity driving this program. However, the bureaucratic efficiency is not the primary reason for the sleepless nights currently being experienced by foreign military strategists. That part of the story comes later. First, it is necessary to understand precisely what LUCAS is and its lineage. On the surface, LUCAS holds no mystery for anyone who has followed the trajectory of modern warfare in Eastern Europe. It features a delta-wing airframe, a rounded nose cone, and a rear-mounted pusher propeller. Visually, it is nearly identical to the Iranian Shahed 136 loitering munition. According to statements made to defense publications in December of 2025, a United States official confirmed that the military had obtained an Iranian Shahed airframe, subjected it to a rigorous reverse engineering process, and handed the resulting design package to Spectre Works. The LUCAS drone is the direct product of that engineering effort. It adheres closely to the Shahed blueprint at a unit cost of approximately $35,000, with a range of 444 nautical miles, a payload capacity of roughly 40 pounds, a cruise speed of around 74 knots, and the ability to carry approximately 18 kilograms of explosives. LUCAS occupies the exact same cost-effectiveness niche as the weapon that inspired it. As one Navy captain explained during the initial rollout, LUCAS is a low-cost, scalable system that provides cutting-edge capabilities at a fraction of the cost of traditional long-range United States systems that can deliver similar effects. The notion of the United States reverse engineering a weapon from a strategic adversary is, in itself, a remarkable inversion of historical precedent. For decades, the flow of technology went the other way. Iran reverse-engineered the Tau missile into its own anti-tank variant in the 1970s. It derived anti-ship missile families from captured Israeli weapons in the early 2000s. In 2011, A sophisticated American surveillance drone strayed across the Afghan border and landed intact in Iran, and within years, new radar-evading drone designs proliferated throughout the Iranian military arsenal. The Shahed 136 itself appears to have roots tracing back to an Israeli loitering munition design, which further traces back to a German Cold War-era anti-radar concept. Reverse engineering has long been an unofficial pillar of certain military-industrial complexes. So when the United States turned the tables, not only reverse engineering the most widely deployed enemy drone weapon, but also using it against its own creator in its first combat outing, the strategic irony was lost on absolutely no one. A senior spokesperson for the adversary's military apparatus attempted to spin the development, telling state media that there is no greater honor than seeing self-proclaimed superpowers kneel before a domestic design and copy it. But the bravado rang hollow because within hours of that statement, Lucas drones were already striking targets across the region. According to defense acquisition analysts, this was entirely by design. When the relevant combatant command established a specialized task force in December of 2025, a defense official indicated that the unit was specifically set up to flip the script. The psychological value of using an adversary's own weapon concept against them at comparable cost, but with dramatically superior internal electronics, was a deliberate factor woven into the operational planning. So far, what has been described as a clever bit of engineering and a satisfying dose of battlefield irony. What it is not, at least not yet, is a revolution. Certain nations have been firing Shahed-type drones and their domestically produced analogs by the tens of thousands since the escalation of hostilities in early 2022. As of November of 2025, independent estimates suggested that approximately 5,400 Shahed-type drones had been utilized in a single theater in that month alone, averaging roughly 182 launches per day. Industrial facilities have been churning them out at a massive scale. A jet-powered variant has since entered service. The adversary knows this platform inside and out. A Lucas flying toward a target in a vacuum would not represent anything structurally new or particularly frightening. But a Lucas is not flying in a vacuum, and what it carries on its back changes everything. Close examination of footage from a sea-based test launch of Lucas in mid-December of 2025 reveals a critical detail. The test occurred from an Independence-class littoral combat ship in the Persian Gulf, marking the first ship-based launch of the platform. On the top of the drone, a small communications box is visible. It is easy to overlook without the proper context. Foreign open-source analysts did not overlook it. Within hours of combat imagery circulating online from the late February operation, those analysts had identified the box for what it almost certainly is: a terminal connecting to a vast, low-orbit satellite communications network. Commentary aggregated from several prominent military channels sounded the alarm with an unusual level of candor. The reaction in professional military circles was swift and visceral. One influential channel summarized the fear with unusual directness. What was inevitable has happened. These terminals have been installed on American drones, allowing jam-resistant communication anywhere in the world where the network operates. The effectiveness of enemy drone strikes will increase by an order of magnitude. Another channel was equally blunt, asking what is there to see but a receiving antenna which will allow the drone, if it is not shot down, to be guided precisely to its target while remaining connected until the very last split second. A third commentator made the logical next step explicit. All these long-range strike systems will be able to be controlled anywhere on the planet and achieve the same precision as first-person view drones, literally through a window. To understand why these analysts are genuinely alarmed and not merely performing for their audiences, one must understand why this new guidance method is so different from what has been fought against and won against for the past 4 years. Since the start of the decade, both sides of the ongoing conflict in Europe have mastered the art of electronic warfare against satellite navigation-guided drones. The logic is straightforward. Navigation satellites, of which there are 31 in the primary American constellation, orbit at around 25,500 miles above the Earth. The signals they transmit are relatively narrow band and low power. By the time those signals reach a drone flying at low altitude, they are incredibly weak. Jammers exploit that weakness by producing a stronger signal in the same frequency band, effectively drowning out the authentic signal. The drone goes off course, crashes, or can even be redirected and captured. A sophisticated mobile jamming architecture has been built around this principle, including truck-mounted systems that have proven effective not only against drones, but against guided munitions as well. As one commander described the dynamic, the enemy plays with frequencies, and the defenses reconfigure the electronic warfare systems. The enemy begins to suppress the defensive systems with electronic warfare, and the frequencies switch again. It is a constant iterative game of measure and countermeasure built on the fundamental exploitability of distant, low-power navigation signals. The new satellite network breaks that game at its very foundation. It is not a navigation system, it is a communications network. It operates in low Earth orbit, not over 12,000 miles up, but roughly 341 miles above the surface. As of mid-March 2026, the milestone of over 10,000 active satellites in this specific constellation was reached after a routine launch from the West Coast placed more units into position. Including all launches since mid-2019, the total number of these satellites placed in orbit exceeds 11,000. These satellites are moving at close to 17,000 miles per hour, forming a constantly shifting mesh that provides near ubiquitous coverage. A terminal does not lock onto one satellite and hold it. It continuously hops across the constellation, bouncing between units as they pass overhead. At any given moment, the terminal is likely managing connections across multiple satellites simultaneously, switching on sub-second time scales. This creates two catastrophic problems for traditional electronic warfare. First, the defender is not trying to jam a single signal vector. They are trying to jam a moving target placed on a constantly reconfiguring network. The geometry changes faster than a lock can be established. Second, because the satellites are so much closer to Earth than navigation satellites, the signal arriving at the receiver is dramatically stronger. Drowning it out requires jammers of a completely different class and power level than anything currently deployed at scale. Some military researchers in the Pacific region have run computational models assessing what it would take to suppress this type of coverage over a specific contested island, something identified as a critical precondition for any successful amphibious operation. Their conclusion indicated it would require an optimal grid of at least 935 synchronized high-powered airborne jammers. Using lower-powered ground-based systems, that figure might climb toward 2,000 or more. When that problem is mapped onto a theater with a front line stretching 500 to 750 miles, where a defender would simultaneously need to protect millions of square miles of their own territory from long-range enabled strike systems, the scale becomes essentially impossible. And that is before factoring in the encryption. The network employs spread spectrum modulation, a transmission technique that distributes signals across a wide range of frequencies in a pattern that shifts constantly based on a cryptographic key. Jamming one slice of the spectrum means you have likely only hit noise. To fully suppress the signal, an adversary would need to overpower the entire frequency spread simultaneously. Even then, without access to the key management infrastructure, which is classified and tightly held, it is impossible to predict or decode the pattern. For practical purposes, the system is locked out. It is worth pausing to ask how the situation reached this point so quickly. The answer involves a subplot that is just as important as the Lucas story itself, because the opposing force actually attempted to use this same satellite network first. Defense intelligence in the summer of 2025 flagged the threat after recovering debris from Shahed-type drones fitted with the same terminals. A respected electronic warfare analyst confirmed that forces had begun equipping their kamikaze drones with these terminals and mesh relay systems. Their first efforts in early 2025 were unreliable and vulnerable to jamming. But within 5 months, they began actively testing the system with dramatic results. Defenders confirmed the equipped drones were effectively immune to conventional jamming. As one expert stated plainly, 1 in every 3 drones managed to hit its target because of this network. It is impossible to suppress them with electronic warfare. They can only be shot down physically. The capability was extended beyond long-range drones to cheap plywood models that gained dramatically extended range and precision, penetrating deep into protected territory, largely immune to jamming systems that had been perfected over years of war. The situation deteriorated to the point where, in late January of 2026, a guided drone struck a civilian passenger train, resulting in multiple casualties. That attack triggered a decisive response. In late January and early February of 2026, the network operator implemented a whitelist system for terminals in the active combat zone. Terminals that could not be verified were rendered inoperative. The consequences for the attacking forces were immediate and severe. The shutdown led to a massive collapse of frontline command and control systems. Without the network, forces lost the ability to coordinate attacks, adjust artillery, and effectively control their drone fleet in multiple sectors. Traffic in occupied territories fell by roughly 75% following the enforcement action. This sequence of events reveals a crucial truth. Both sides recognize the game-changing value of these guided weapons. One side tried to exploit it through unauthorized and unsecured terminals and was cut off. The other side, the United States, built it into a purpose-designed weapon system from the ground up. There was no reaction to the technology on drones. There was a plan for it. That is the institutional asymmetry at the heart of this story. The Lucas program is also deliberately a proof of concept for a completely different model of defense acquisition. The Deputy Director of Experimentation in the Office of the Undersecretary of War for Research and Engineering made it explicit that SpectreWorks is not the sole Lucas manufacturer. The design was architected from day one for production across multiple vendors. The defense leadership announced a multi-year drone buy, requiring manufacturers to compete in what the Pentagon calls gauntlet challenges, head-to-head operational evaluations rather than traditional bureaucratic procurement processes. Under the broader Drone Dominance Program, funded at over $1 billion through recent legislative acts, the goal is procurement of hundreds of thousands of drones by 2027. Phase 1, announced in early February of 2026, selected 25 vendors competing for $150 million in delivery orders for 30,000 drones at $5,000 per unit, with deliveries expected by July of that year. Subsequent phases aim to drive unit costs down further, potentially as low as $2,300 per unit. That is not a misprint, $2,300. At those volumes and those prices, the cost calculus of drone warfare inverts completely. An adversary cannot intercept swarms that size fast enough, cannot manufacture interceptors cheaply enough, and cannot absorb the attrition of their own air defense systems being overwhelmed by sheer volume. A former Navy Rear Admiral, now a defense advisor, explained the targeting philosophy clearly. You do not send Lucas after a hardened bunker. You send it after the radar protecting the bunker or the fuel depot keeping the Air Force flying. That is how one blinds an adversary before the expensive weapons arrive. And the Lucas is not flying alone. The platform integrates with what is described as a multi-domain unmanned systems communications network, enabling the drone to serve not only as a strike asset, but as a communications node. In a swarm architecture, a smaller number of equipped hub drones coordinate the strike package, while the rest of the swarm follows their targeting data. It is not necessary to have a terminal on every single drone in the swarm. It is only necessary to have enough to make the entire swarm impossible to neutralize electronically. Former drone operators have explained that Lucas drones are typically deployed in swarms of 4 to 10 units. Coordinating dozens of those swarms under a connected command architecture creates a distributed strike capability that no existing defensive infrastructure was designed to handle. What can an adversary actually do about this? It is a question being asked loudly in military circles, with few satisfying answers emerging. The most obvious path, kinetic attacks on the satellite constellation itself, is not viable at any foreseeable scale. As one prominent blogger noted, the old Soviet tales about nails scattered in orbit sweeping away satellite constellations might have worked against hundreds, but not against tens of thousands of satellites. Some analysts have acknowledged the problem directly, demanding the development of means to destroy thousands of these satellites, and insisting this must be funded as the highest priority. However, where the money comes from for such an endeavor in a wartime economy already straining under sanctions and massive military expenditure is a question left unanswered. The independent tracking of equipment losses has already recorded at least 94 jamming and deception systems destroyed or captured since 2022. One cannot build a suppression architecture if the existing electronic warfare infrastructure is being steadily eliminated. There are two systems under development that deserve attention. The first is a repurposed platform originally designed to protect domestic satellites from jamming, which has been redirected to disrupt communications and navigation. Leaked documents suggest at least 3 installations have been specifically deployed to target the new network over contested territory. The second and more concerning is a system that state media has called a Starlink killer. Developed by a National Center for Unmanned Systems and Technologies, this system is specifically designed to detect and disrupt signals to and from the low-orbit satellites. The director of that center has claimed the system can identify connected devices within a range of up to 15 kilometers and has stated publicly that the detection capabilities extend to the militarized version of the terminal. What makes this particularly worrisome is not just the jamming claim, but the ability to identify specific terminals, potentially allowing forces to geolocate and strike equipped assets directly rather than simply trying to overpower their signals. The deepest lesson of the Lucas story is not about a single drone. It is about what happens when the infrastructure of a civilian economy, a satellite internet network, a startup culture, and an acquisition system willing to move fast becomes indistinguishable from military capability. The United States did not build Lucas in a defense laboratory over a decade. It captured an enemy airframe, handed it to a startup in Arizona, and fielded a combat-ready system in 43 weeks, running on a commercial satellite network that 10,000 satellites make effectively unjammable. That is the new template, and the template is not going away. The gap in commercial satellite investment is a structural deficit that spans a 30-year lead time. One side spent over 10 years and billions of dollars in private capital building this constellation before it became a military tool. The opposing nations are now trying to replicate that investment on a compressed timeline against a moving target that keeps getting larger. By the time the competition reaches a few hundred satellites in their own constellations, the existing network may have 15,000 or more. The acknowledgement from within the adversary's own military apparatus that there is currently no solution, not an incomplete solution, not a developing solution, but no solution, is an admission of a deficit that cannot be closed by mere tactical adaptation. It is a deficit built into the very foundation of how modern technology is funded and deployed.